The next contribution is entitled The Magnetospheric Influence on the Diurnal Variation of the Ionospheric F region during Geomagnetically Quiet Times by Ray Roble.
Today I would like to describe a ionospheric model that may be used to deduce the ionospheric magnetospheric interaction primarily through its influence on the F region parameters, namely the electron temperature, ion temperature, and electron density. The first slide shows the general outline of the model. Basically, I start with a solar EUV flux measurements by Hinneregger. It creates a primary photoelectron spectra from 1 to 100 electron volts. The primary photoelectron spectra then goes into a photoelectron transport equation. Okay. Could we focus this on? Okay. The secondary photoelectron transport equation developed by Nagy and Banks, and therefore at each time step and each altitude one can calculate a photoelectron spectrum, fold it into the appropriate air glow excitation cross-section. One can calculate the air glow excitation rates, calculate the photoelectron heating, which then goes into the coupled electron-ion energy equation to calculate the electron-ion temperatures. In addition to that, from the magnetosphere, we need a flux of electrons, or a flux of heat in the electron gas and in the ion gas. There is also a plasma transport between the magnetosphere and the ionosphere that enters into the continuity equation. The continuity equation solves for 5 separate ion species, NO+, O2+, N2+, and 2 oxygen ions. The O+ is considered as a major ion and diffusion is allowed. We have a nighttime ionization source. The dotted line indicates a separation. The neutrodynamics is not included into the dynamic calculations, but the winds and the temperatures are deduced from a separate model based on incoherent scatter observations, so that it forms a consistent type of wind that goes in to specify the plasma drift up and down along the geomagnetic field line. Other things is we can excite air glow lines through thermal excitation, recombination, and then EUV air glow absorption can go back into creating a primary photoelectron spectrum. The next slide will summarize, the next slide shows the type of boundary conditions that are used in the model. We have here John Evans's measured electron temperature for March 23 and 24, 1970 at an altitude of 800 kilometers. The electron temperature rises near sunrise, decreases to a plateau region here around noon, and then another increase around sunset, and then drops to low nighttime values. And the ion temperature boundary conditions are illustrated here. The O+ flux goes with this coordinate here, upward flux generally through the day, a large increase during sunset, and then a downward flux at night. And these are the boundary conditions that go into the O+ plasma transport equation. Some of the results here, comparing to March 23, 24, the left-hand side here indicates the electron temperature as measured by John Evans in the slide that he presented earlier in the day for March 23, 24, 1970. The diurnal variation, and this slide here illustrates the calculated values from the model. It shows the characteristic feature of the increase in temperature at around sunrise, decreasing to lower values during the daytime, and then again another temperature increase, and you can see it as a heat flow penetrating to lower altitudes, but because the electron density near sunset is higher, it doesn't penetrate as deeply into the ionosphere, and then at sunset the temperature decreases, but there is always a positive gradient in here indicating a flow of heat from the magnetosphere. The ion temperatures also follow a similar pattern. Basically, below 300 kilometers, we are following the neutral gas temperature, but as we go to higher altitudes, then the Coulomb coupling with the electrons is greater, and the temperature tends to increase. Also, the boundary conditions indicate that there's a flow of heat coming in from the magnetosphere in the ion gas, although it is quite small. The electron density that we calculate here, the observations and the calculations, basically we have a decrease after midnight, following by a morning increase, and then another drop-off. The winds play a very important effect in maintaining the overall structure of these contours of the ionosphere. The dash curve here indicates the altitude of the F2 peak, showing a lifting during the nighttime hours, primarily maintaining the ionization in the high altitudes so that recombination is relatively slow, and thereby maintaining the nighttime F2 region. Some of the output here that one can get out is calculate the neutral gas heating function. Basically includes effects from solar Schumann-Runge heating and photoelectron heating. And also one can calculate the lambda 6300 volume emission rate of the air glow. The next slide shows the relative contribution as a function of time. Air glow 6300 in Rayleigh, the total, the contribution due to photoelectron excitation, the contribution to Schumann-Runge, dissociative recombination, and thermal. So all these can be dissected in the model. And here we show the 5577 emission. Now for this conference, I primarily shut off the magnetospheric influence to see just how much of the magnetosphere will maintain the ionospheric temperatures in the F region. And in this case, there is no flow of heat coming in from the magnetosphere. This is the calculation that was similar to John Evans's measurements. And it indicates a rapid rise during sunrise due to the fact that there's photoelectron heating and a general temperature pattern maintained during the daytime. But as all nighttime sources decrease, then the electron temperature will approach the neutral gas. So the thermal structure above, about 300 kilometers, is primarily maintained by a flow of heat coming down from the magnetosphere and determined by the specified boundary conditions at 800 kilometers. But the thermal structure below 250 is primarily determined by the solar photoelectron heating. Well, one can determine the amount of heat necessary to bring the calculated solar photoelectron heating into agreement with Evans by assuming a magnetospheric heat flux, and one can get an idea of the diurnal variation of the magnetospheric heat flux. Basically, after sunset, there is a rapid decreasing through the night, then at sunrise, a rapid increase, a level plateau during the early morning. In the afternoon hour, it rises to a maximum around sunset and then decays. Now, this plus the solar heating is the amount of heat necessary to bring the plasma temperatures up into agreement with what John Evans has in this. Basically, let's see, the electron or the energy coming in is about, the peak value is about 1.3 times 10 to the 10th. The diurnal average is 7.5 times 10 to the 9th EV per square centimeter per second coming through. This slide shows the influence of the electron density shutting off any plasma transport between the magnetosphere and the ionosphere, and gives an indication of what is the mechanism necessary to maintain the ionospheric structure throughout the day. And there's very little difference between the case with a small plasma flux coming into and out of the upper boundary here, and in this case, and this is primarily, the ionospheric structure is primarily maintained by neutral winds forcing ionization up and down along geomagnetic field lines, and only the very topmost part is influenced by the O+ flux coming in and out. In general, the O+ fluxes are quite small compared to other days.
No flux?
No flux. Right. The last slide here, I ran a case for the Tecnica Latitude at 65 degrees. Once again, this is the solar ionosphere. There is no magnetospheric influence at all. The temperatures will rise early in the morning. Generally, the sun rises early because this is March 23, 24, 1970, or equinox cases. The temperature would look like this. The electron density rises, and because the electric field is, or the magnetic field line is perpendicular to there is no component of wind forcing ionization up and down along geomagnetic field lines, and as a result, the electron density will drop off much more rapidly, not maintained at all by the winds, and the F2 peak is generally constant. So any departures from these particular curves should be due to magnetospheric type influence, which might give us some indication of what type of processes may be acting in there.
Great. The nighttime things here, you show an infinite temperature gradient essentially at night in the vertical rig. Are those plotted right?
Yeah, these are constant. It's basically the neutral gas temperature. The 1,000 contour goes this way, and the temperatures here will be about 900, 950 degrees. Yeah, okay.
If I interpret your slide correctly, the influence of the magnetosphere on the O plus concentration in the ionosphere seemed to be very little.
For this particular day, yes, there's very little influence on the O+, and the magnetospheric influence is primarily in maintaining the thermal balance in this particular case.
Does this tally up with Park's observations of the flows in the Britonosphere, or with, say, Peter Banks's observation of large fluxes?
I can get significant variations in the electron density by specifying higher fluxes in and out. And if one wants to, one can specify a very large flux and actually empty out the ionization. And in this particular case, about 10 to the 7th, the influence is relatively small, only in the top side F region.
Yes, I noticed that you haven't put you have H plus on I think the first slide, but it wasn't clear just what influence the H plus had on the solutions.
The H plus at the present time is considered as a minor ion. So, and its flux is not known, it's set equal to 0. So that it's just the O plus flux that is coming in and out of the Britonosphere.
Okay. You say you use the O plus fluxes that we see at 800 kilometers. Yes. But those are sort of neither fish nor fowl. I mean, the peak flux that the O plus reaches is usually seen lower down at, say, 600 kilometers. Mm-hmm. And by the time you've got up to 800 kilometers, some of the total flux, either from the ionosphere into the magnetosphere or vice versa, is now being carried by protons, which we don't see.
Yes.
So you may be taking too low flux values, especially at night.
Yes, I agree.
Your ability to reproduce the temperature and density profiles is really astounding. What solar EUV flux values did you use here, Ray?
Okay, I'm using twice Hinneregger solar fluxes, and I'm using an atomic oxygen concentration of about 10 to the 11th at 120 kilometers. So to make this model work, one has to tune the solar flux. The overall shape of the contours is really very strikingly determined by the neutral wind. So one very carefully has to evaluate what the component of the neutral motion along the geomagnetic field line is. And then the shape of the contours can be reproduced. In addition, the electric field also has an influence on tilting the shape of these contours, and this may make a contribution.
This really speaks well for what one can do with one-dimensional modeling, I think. Really.
During quiet times, perhaps.
I think it's only fair to point out also that there are many other calculations that for which one has to double the solar fluxes, as you did. Mm-hmm. Maintaining the global exospheric temperature in the neutral atmosphere, photoelectron escape fluxes, and other things also.
Yeah. Well, perhaps we will learn more from AE when it gives us results.
Rishbeth, have you tried to see whether you could get the maintenance of the F-layer at night during the winter? Because I think that might be a harder job.
So far, I've been concentrating on the one day during equinox. Things are simpler there and it's quiet and so forth. John has supplied me with data for a winter case, and I will be looking at that shortly. Mm-hmm.